Hi, everybody, and welcome to our next lecture in CHY 113. We're up to lecture 9 now at this point, starting to get a little bit deeper into Unit 2. And so, with that being said, let's go ahead and just dive right into our warm-up questions for today. And so, to begin, let's go ahead and try to do this calculation. So, we are given a chemical reaction here, a balanced chemical equation, and we want to calculate how much of our precipitate, how much of the calcium carbonate will form given a starting amount of 3.48 grams of sodium carbonate. And we're told there is plenty of calcium nitrate to react that with. That will make a lot more sense after today's lecture when we start getting into limiting reactants. And so go ahead and pause the video now and see what you can come up with for an answer to this question. Hopefully you were able to come up with 3.29 grams of calcium carbonate. Let's go ahead and go through this. And so we are given, just shrink this a little bit more so I have more of my whiteboard to work with. And so 3.48 grams of our sodium carbonate. It's our starting amount. So remember our basic pathway, we always need to find a way to get to moles of whatever it is that we're given. And we're given grams in this case, so we can simply use our molar mass. So our molar mass of sodium carbonate, 105.99 grams. And I just calculated that before starting up the lecture here. So now we have moles of what we were given. Next, we can use our balanced chemical equation to come up with our stoichiometric ratio to convert from what we were given to what we're looking for. We see from our equation that for every 1 mole of Na2CO3 that I start with, I form 1 mole of my calcium carbonate, my CaCO3. Then finally, our last step is we're looking for how many grams of calcium carbonate will form. And so we're going to use our molar mass of calcium carbonate. We plug all of this into the calculator, and we'll just double check my calculation from before. 3.48 times 100.09, all divided by 105.99. And sure enough, .29 grams of CaCO3. And there we go. For the next problem, the next warm-up question, you need to start to draw in all of the material actually that we learned in Unit 1 and start to tie a lot of different things together. And so for this question here, we have a reaction of 255 milliliters of 0.25 molar aqueous sodium phosphate and an excess amount of calcium nitrate. So we want to predict how many grams of the precipitate will form. And so that's all I'm going to say about this one. We will work through it. But I want you to go ahead and pause the video now and put together a lot of what we learned in Unit 1, put it together with what we talked about in the last lecture for stoichiometry, and see what you can come up with for an answer. Hopefully, you got 9.88 grams of calcium phosphate with the correct formula for calcium phosphate shown. And so let's talk about how we approach this. So in order to even do a stoichiometry problem to begin with, we need to start with a balanced chemical equation and looking at our reaction. So let's go ahead and start there. So we're told that aqueous sodium phosphate, and so we have to come up with our chemical formula first for sodium phosphate, sodium with its 1 plus charge, and phosphate with its 3 minus charge. And so we will have a formula of Na3PO4, and we're told that that is aqueous. That's reacting with our calcium nitrate, calcium with its 2 plus charge, nitrate with its minus 1 charge, so a formula of CaNO3 2. Now we need to determine what our products are going to be. So there's different ways to approach this. Remember, our positive ion from one is going to come together with our negative ion from the other, and vice versa. And so we recognize that sodium is our positive ion in the first equation, or the first formula. Nitrate is our negative ion from the other. Calcium is our positive ion here, and phosphate is our positive ion here. And so those are going to be our new plus minus combinations. Somebody in the bright space discussions had a great way of looking at this that honestly I had just never thought of it this way. The one way you can think of it when you're looking at these sort of double displacement reactions is that the inners are going to come together with the inners, and the outers are going to come together with the outers. And that's a great way to think of it too, because that definitely will work out to be the case. And so let's go ahead and just take a peek at those. And so Na is coming together with NO3. Positive 1 is our 1 plus from Na, our 1 minus from NO3. So a plus 1 and a minus 1 is just going to be NaNO3. Calcium with its 2 plus, phosphate with its 3 minus. So our formula there is going to be Ca3, PO4 2. Let's just clean this up just a little bit. Okay, so there's the beginning of our formula now, of our equation. Next, we need to balance it. And so in order to have a correctly balanced equation here, we need 2 Na3PO4s, we need 3 of our calcium nitrates, and we need 6 of our NaNO3s. Now we have a balanced equation. Lastly, we need to apply our solubility rules to figure out what's going to be our precipitate. And so remember, from our solubility rules, all compounds containing sodium and all compounds containing nitrate are going to be soluble with no notable exceptions. So NaNO3 is certainly aqueous. Phosphates, however, the majority of phosphates are not soluble, and calcium was not one of our exceptions to that rule. So phosphates are insoluble, calcium's not an exception to that, and so there's our precipitate. Our calcium phosphate will precipitate out of this. Now we're finally ready to apply the stoichiometric processes that we talked about in our last lecture. So remember, the first step is to be able to convert our given amount over to moles. Now in the last example, we had grams of our given amount, so we could use our molar mass. Here, we have a volume of our given amount in a molarity, so that's what we're going to use. And so we're starting with 255 milliliters of the sodium phosphate. Remember, the units of molarity are in liters, so we do have to convert over to liters. But now we're ready to use our molarity. That was the 0.250. Remember that the units of that are moles per liter. So that is 0.250 moles of the sodium phosphate per liter. Now we can apply our stoichiometric ratio from our balanced chemical equation. We see from our balanced equation that our relationship is 2 moles of Na3PO4 to 1 mole of our precipitate. And this is what we know that we're looking for, the Ca3PO42, because the question asked us for the grams of precipitate, which is definitely going to be our calcium phosphate. So that's a 2 to 1 ratio. So we have 2 moles of sodium phosphate to 1 mole of the calcium phosphate. Lastly, we can now convert over to grams of our calcium phosphate using our molar mass. We know that the molar mass of calcium phosphate, I calculated it before starting the video, It's 310.18 grams of calcium phosphate per 1 mole. Now we're ready to plug all that into the calculator. Let's just double check my calculation. 255 times 0.250 times 310.18, all divided by, and bottom, making sure I use parentheses here in my calculator from doing the calculation all at once. 1,000 times 2, close parenthesis, and sure enough, I get 9.88. Sorry, rounding, a little bit different. Should be 9.89. But our 9.89 grams of calcium phosphate. And so I really liked this question, and I wanted to throw this one at you to show how things are building up, and that we are still going to be using everything that we did in Unit 1, and now we're applying it in some different ways. And so that this question really starts to show us how we're putting things together now. And so let's go ahead then and now move into our topics for today. And so our big thing that we've been making a big assumption so far with our stoichiometry problems. What we've been doing is, and some of these have been built into the problems, but we've been assuming that we have enough of the other reactant in our problem for the reaction to take place. And that's not going to be the case all the time. Or to put it another way, there's always going to be an amount of one of the reactants that will limit how much product is actually being made. And so remember, and actually I talk about this more in some of the next slides. So actually let's hold off just a minute. So we're going to talk about something called limiting reactant, and then we're going to briefly discuss yield of reactions and percent yield. And so there will always be an insufficient amount of one of the reactants to consume the other completely. And so, like I had mentioned earlier, think maybe in terms of recipes. So we can think of a chemical equation like a recipe of some sort. And if we're making our cookies, you know, maybe your recipe is calling for so many cups of flour, so much butter, this and that. And let's say you've got oodles of all that. You've got tons of all that sitting in your cupboard. You have tons of all the ingredients, but then you realize you've only got a quarter bag of chocolate chips left. Those chocolate chips limit how many cookies you can make. And that's what we're going to be looking at here with our limiting reactants. We're going to be looking at which reactant limits how much product can be formed. Think of it this way. Think of it if you've got a set of just nuts and bolts. And so if I have 32 nuts and 28 bolts, and a set, let's say, one nut and one bolt, I've got my bolt here, and I put my nut over it. So a set is just going to take one nut and one bolt. So we can look at an equation for that. A nut plus a bolt gives us a nut-bolt complex. And so think about then, how many sets can you actually make? How many complete sets of nuts and bolts can you make? You make 28, right? The number of bolts here limits how many of these complexes you can make. And you're going to have 4 of the nuts left over. You've got 4 of the nuts in excess, 4 more than what you actually need. But we could only make 28 of the total system, so to speak, because we're limited by the number of bolts that we have. Now let's say the same scenario. We have 32 nuts and 28 bolts, but now for whatever we're building, some weird IKEA thing maybe, now each set uses 2 nuts per 1 bolt. So we have to use 2 nuts on this and only 1 bolt. So now our equation becomes 2n plus b gives us our nut-bolt complex. So now ask yourself, how many actual sets can we make? We can only make 16 sets now, right? The number of nuts are what is actually going to limit us. I like to show this example whenever we start to talk about limiting reactants, because what you have to realize for limiting reactants is that you can't simply look at what you have less of and say, oh, well, that's going to limit my reaction. There's more that's going to come into play there, such as the actual stoichiometric ratio that things are going to react in. In this case, I need to have 2 nuts per every set. And so since I need to have 2 nuts per every set, I can only make 16 sets total because I'm limited by the number of nuts that I have. You're going to see the same thing when we start to talk about reactions here in a little bit. You can't simply look at the one that you have less of and say, well, that's going to limit me. Because we'll have things like the actual stoichiometric ratio that is going to factor into that. We also have the simple fact that we have to work within moles for our chemical reactions. And so you can't simply look at the number of grams of something. And so as an example of that, let's say that I have 10.0 grams of H2. Let's say maybe we're looking at our reaction of H2 plus O2 in order to make hydrogen peroxide, something like this. So if I have 10.0 grams of H2, and I also have 10.0 grams of O2, or sorry, let's even change this. Let's say I have 10 grams of H2, and I also have, I'll say 8.00 grams of O2. So again, it's tempting to just look at this and say, well, I've got fewer grams of O2. So that's obviously going to, sorry, and this is what happens when I try to do things on the fly. I want to do that differently. 12.0 grams of O2. There we go. And so again, it's tempting to look at this one and say, well, I've got fewer grams of H2, then that must limit my reaction. You can't simply look at the grams because we don't do a gram to gram comparison. Remember, we do mole to mole comparisons. And so 10.0 grams of H2 is going to equal 4.96 moles of H2, my 12.0 grams of O2, divided by, not multiplied. I only have 0.375 moles of O2. So the O2 is absolutely going to limit how much peroxide I can make here. I have a lot fewer moles of it. So again, I just went through all of that just to, again, really demonstrate that you can't simply look at the gram amounts or the amounts that you're given and say, well, the lesser one now obviously limits me. There's much more at play there, such as converting to the number of moles, looking at the balanced chemical equation, and some other factors which we're going to see. And so we have to keep that in mind as we go through these types of problems. Just another couple examples so we can start to see what's going on here. And so if we have 27 wheels and 12 handlebars, we want to find out how many tricycles we can actually make. So just think about that for a minute. If I have 27 wheels and 9 handlebars, how many trikes can I actually make? Again, let's think of it like a chemical reaction. And so if I'm trying to make 1 tricycle, that's going to consist of 3 wheels plus 1 handlebar is going to make 1 trike. And so based on the number of wheels, I've got 27 wheels. Each trike is going to take 3 wheels. And so that means that I can make 9 trikes based on the number of wheels that I have. I have 12 handlebars. each trike takes 1, so I could make 12 trikes based on my number of handlebars. However, my number of wheels is going to limit that, and so I can only make 9 tricycles, making 9 little kids very happy. And so let's look at how we actually do this in some chemical formulas and some chemical reactions. So here's an example here. And so what is the limiting reactant if we start with 50 grams of aluminum and 50 grams of oxygen, and the two of them are going to react together? So we want to find the theoretical yield for that reaction. Don't worry about the term theoretical yield quite yet. We will be talking about that later today. So we have a reaction of aluminum and oxygen, and we're given 50 grams of each to start out. And so the first thing that we need is our balanced chemical equation. So we come up with our balanced chemical equation for this. So we get 4 aluminum plus 3 O2 give us 2 aluminum oxides. So there's our balanced equation. What we want to do next is to use the number of grams of each to convert that to the number of moles of each. So we're just going to do grams to moles for each of the reactants that we have. So that's all we're doing here. We're taking our 50 grams of aluminum, dividing that by our molar mass of aluminum to come up with 1.85 moles of aluminum. And then our 50 grams of oxygen divided by the molar mass of O2, come up with 1.56 moles of O2. So all we're doing here, all we're doing so far, is we're just converting our given amounts, our 50 grams of aluminum and our 50 grams of O2. We're taking those given amounts and we're converting those over to moles. That's all that we're doing. What we want to do next, though, is we want to compare, we want to come up with a ratio of those two reactants to each other. So all you do next is you take one and you divide by the other. It's a little bit easier probably just to take the larger one and divide it by the smaller, but it doesn't really matter as long as you're consistent in the next step that comes after. That's generally what I do, is I take the larger one and I divide it by the smaller one. And so what that gives me then, what that tells me is that, so if I take my 1.85 moles of aluminum divided by my 1.56 moles of O2, that tells me that my basic ratio of reactants that I'm starting with is, for every 1 mole of oxygen that I'm starting with, I have 1.19 moles of aluminum. So that's what I have. That's what I'm actually starting out with, is 1.19 moles of aluminum to 1 mole of oxygen. Again, that's not the true amount, but that's our ratio. That's condensing things down because we're going to use that as a basis of comparison in just a second. We compare that to what I would actually need according to the balanced chemical equation. Our balanced chemical equation is 4 moles of oxygen to every 3 moles of O2. This is what I mean by being consistent. In this step here, I divided my aluminum by my oxygen. And so now in this next step, I'm also dividing my aluminum by my oxygen. And so this tells me that the ratio that I need is 1.33 moles of aluminum to every 1 mole of O2. So again, let's just be crystal clear about what all these numbers are, because I know where things are starting to jumble a little bit. On the left, that ratio of 1.19 to 1 represents how much we actually have. For every 1 mole of oxygen, I have 1.19 moles of aluminum. On the right, that's how much we actually need according to our balanced chemical equation, according to our recipe. That's how much we need. I need 1.33 moles of aluminum, excuse me, for every mole of oxygen. And so what we can see here is that compared to 1 mole of oxygen, I don't have enough aluminum. This is how much I have. I actually have 1.19 moles of aluminum in a ratio. So in that ratio, I have 1.19 moles of aluminum versus I would need 1.33 if I had 1 mole of O2. This tells us then that aluminum is the limiting reactant, because that 1.19 is less than the 1.33. And so the reason that we just divide it is so that we're comparing apples to apples, so that we're looking at our ratio of saying, okay, if I only had 1 mole of oxygen, this is how many moles of aluminum that I would have, versus what I need. If I only had 1 mole of oxygen, this is how much aluminum I would need. And we see that that amount is less for aluminum. And so that is our limiting reactant. So now that we know what the limiting reactant is, we can take how much we actually had, which was our 1.85 moles of aluminum. That's the real amount that we had. We're going to take our 1.85 moles of aluminum because that's what limits our reaction. And we're going to complete the rest of our process from there. We're going to then use our molar ratio, just a regular stoichiometry problem like we've seen, our 2 moles of aluminum oxide to our 4 moles of aluminum. Oops. And then we're going to multiply that by the molar mass of the aluminum oxide to come up with 94.3 grams of aluminum oxide. And so what we have done here is we have figured how many we have figured out what the limiting reactant is. The limiting reactant is aluminum. Based on that limiting reactant, 94.3 grams of aluminum oxide is how much we can actually make. This also means, to throw some more terminology out there, this also means that O2 is our excess reactant. We have more than enough O2. We'll have some O2 left over. When we look at another way to look at limiting reactant problems in just a minute, we'll see how we can actually figure out how much O2 is left. There's a fairly easy way to calculate that. And so this is one approach. We're going to look at a few different approaches to limiting reactants today, because some of you will find that this sort of comparing your ratios of have versus need, some of you will find that works out great for you. Other people will find that this method here is a little bit easier. This is honestly how I learned it when I first learned this. Oh God, now I'm doing math, 20 years or so ago. The way that I learned it was essentially take both of your starting reactants. So take your 50 grams of aluminum and just do out a full stoichiometry problem and figure out how much aluminum oxide you can make based on 50 grams of aluminum. Then do another completely full stoichiometry problem all the way through and figure out how many grams of aluminum oxide you can make based on 50 grams of O2. And so that's what we see here. Is we just see a full-on stoichiometry problem, just like we've been doing so far. And so our 50 grams of aluminum, we convert that to moles. We use our molar ratio between Al2O3 and Al, and then finally convert to grams of Al2O3. And so 50 grams of aluminum will make 94.3 grams of aluminum oxide. We do the same down here, 50 grams of O2, we convert to moles of O2. We use our molar ratio between O2 and Al2O3. And then our molar mass of Al2O3 to see that based on 50 grams of oxygen, I can make 106 grams of Al2O3. Now, I know, though, that I can't make 106 grams of Al2O3 because my amount of aluminum is going to limit me to 94.3. And so if you take this approach, if you simply do a full stoichiometry problem for both reactants, all you do then is you take the one that makes less, that's how much you can actually make, and that reactant was your limiting reactant. So we know that we can only make 94.3. We can't make 106 grams because the amount of aluminum we have doesn't allow us to make that much. And so that's another approach to limiting reactants. Let's look at one more. And this is another really good setup that I like. And some of your, we'll look at reaction yields in a minute. Here we go. This is the one. And so this is an approach that you're going to see in some of your Chem 101 homework. And it's another approach that I like using a table to start just organizing things. And I like this approach for just that organizational approach that it takes. This is called a BCA table, or that's what Chem 101 is calling it. And I don't remember if that's in your textbook or not. But you might also see, just if you're looking at other methods of this, if you just Google limiting reactant table, you'll see a few different techniques. I found a great video. I forget who made it. But a great video that somebody had put together, else had put together on using tables like this. It just gives us a nice way to organize all of our information. And so in this question here, we're told aluminum oxide is used for heartburn relief, things like sour stomach and peptic ulcer and so forth. And so what we want to know, so this is an equation for the formation and the preparation of aluminum oxide. We can make it from aluminum sulfide plus water. It's going to form our aluminum hydroxide and plus some hydrogen sulfide. And so in this particular reaction, we're given 25 grams of aluminum sulfide and 15 grams of water. And so we want to, ultimately what we want to do here is calculate, you can see here, we want to calculate the mass of the products formed and the mass of the excess reactant. So ultimately what we want here is we want to know the mass of both products and we want to know the mass of our excess reactant. And so this sort of table gives us a great way to find everything, to find all of these different masses. And so the first thing that we need to do is we're going to take our, and I actually haven't done this out yet, so I'm going to be doing it along with you. And so we need to convert our given amounts over to moles. So before the reaction starts, we have 25.00 grams of aluminum sulfide. And so we need to calculate the moles of aluminum sulfide. We're given our molar mass right there. That's handy. And so let's just do that here real quick. So we're going to take our 25 grams of aluminum sulfide. Let's make this a little bit bigger so you can see it. And we're just going to convert that over to moles. We're given the molar mass of aluminum sulfide at 150.18. And so we get 25 divided by 150.18. 0.1665. And we see, sure enough, that's one of our options here, so that's great. So that's the number of moles that we have of aluminum sulfide to start out. We'll do our same calculation for water. We're told that we start with 15.00 grams. Molar mass of water, 18.015 grams. So 15 divided by 18.015, 8326. Sure enough, 0.8326. So those are our starting amounts of our reactants. Now, before the equation begins, or before the reaction starts, I don't have any moles of my product. I've got no moles of product at this point. So now what we need to do, though, is we need to figure out our limiting reactant. There are a couple of ways to go about this. You can go about it sort of in the way that we've already done and figure out the limiting reactant and then fill in these after amounts. We're going to go over another approach, though, that I also like when it comes to using these tables. We know that whatever reactant is our limiting reactant, when the reaction is done, the amount of that reactant is going to equal 0. We will have used it all up. That's one of the definitions of limiting reactant. So we will have used all of the reactant up. And so we know that the amount of limiting reactant after the reaction is done, is going to be equal to 0. And so what I would do with this approach then is just choose one of them. It might not be right, and we're going to see how we'll find that, but choose one of them to say, well, this might be the limiting reactant. So let's start with the aluminum sulfide. That means that after the reaction is over, the amount of aluminum sulfide will have been 0. If we started with 0.1665 grams of aluminum sulfide and we end up with 0, that means our change had to be negative 0.1655 moles. Now what we have to recognize here, though, is, again, our ratio. For every 1 aluminum sulfide used, I use 6 waters. So if I'm going to use up 0.1665 moles of aluminum sulfide, I will use 6 times that amount of the water. And so 0.1665 times 6 would be a change of 0.999. Now, for one thing, we look at our Chem 101 options and we see that negative 0.999 isn't even an option. So that tells us that that's probably not right. But the other way that we can look at that is we can say that, well, in order for aluminum sulfide to have been the limiting reactant, that means that I would have had to have also used 0.999 moles of H2O. I do not have 0.99 moles of H2O to start out. I have 0.8326 moles of H2O to start out. And so that means that aluminum sulfide cannot have been our limiting reactant. Aluminum sulfide, if aluminum sulfide was our limiting reactant, that would cause us to use more water than we have. So aluminum sulfide could not have been our limiting reactants. Let's get rid of these. That tells us that water then likely is the limiting reactant. So we're going to go ahead and set our change, or our total of water after the reaction, to 0. That means that water would have had to have been reduced by an amount of 0.8326. And so if we look at how much aluminum sulfide that would have meant, so if I am losing 0.8326 moles of water, for every 6 moles of water, I use 1 mole of Al2S3. So my 0.8326 divided by 6 is 0.1388. And so sure enough, I'm going to use 0.1388 moles of my aluminum sulfide. And so to put that in for my after, the actual amount, I'm just going to go ahead and subtract those. 0.1665 minus 0.1388, 0.0277. Slight difference in rounding, but there it is there. So this tells me then, remember I talked about we can use these tables to figure out how much of the excess reactant remains. This is how we do it. Now I know that after the reaction is done, I still have 0.02773 moles of aluminum sulfide. I can convert that over to grams of aluminum sulfide, which is in fact something I'll have to do. So I'm just going to start keeping track of those here because I'm going to lose it on the next screen. But I know that I'm going to have 0.02773 moles of my aluminum sulfide remaining. Let's look at our others then. So we're also going to need to calculate the amount of both products for. So again, we now know what our change was for water. And since these are all stoichiometric amounts, law of conservation of mass applies. If I am going to lose, let's think of how to write this so that I leave plenty of space for everything. I'm going to lose 0.8326 moles of water. If we then compare that to our moles of aluminum hydroxide, for every 6 moles of H2O that I use, I form 2 moles of my AlOH3. So 0.8366 times 2 divided by 6. So I'm going to form 0.2789 moles of aluminum hydroxide. And that is not one of our options here. Why not? Oh, see my typo or see my mistake? Easy to do, 8326, not 66. And so we get 0.8326 times 2 divided by 6, 0.2775. There it is. So our change is going to be 0.2775 moles of aluminum hydroxide, which means that I'll be left with 0.2775 moles of aluminum hydroxide. Then we do the same thing for our hydrogen sulfide, base it on the amount of water that we actually use. I did it again. So we use 0.8326 moles of water. Our molar ratio tells us that for every 6 moles of water that we had, we formed 3 moles of H2S. .4163 moles of hydrogen sulfide. So I started with 0. My change was 0.4163. So I end up with 0.4163 moles of hydrogen sulfide. So there's my complete table. I'm not done yet. Remember, because I'm looking for everything in this problem. That's why this one is so much different. I'm looking for all of my masses. And so we have all of our after amounts here, and I've written these down here. And so next, as we move on into the table, we want to find that mass of the aluminum hydroxide, the mass of the AlOH3 that is actually formed. And so we do have our moles of AlOH3. We've got that right here. So there's our moles of AlOH3. And we're given our molecular mass. So if I'm converting from moles to grams, I'm going to multiply. So 0.2775 times 78.004 gives me 21.64. Little difference in round, actually 21.65 grams of aluminum hydroxide. Next, my mass of the H2S that is formed, 0.4163 moles. 0.4163 moles times its molar mass of 34.0809 gives me 14.19 grams of hydrogen sulfide. Now, I guess this one actually doesn't, it does ask us for the grams of excess reactant, but there's no place for us to input it. And so we did calculate in our table earlier, 0.02773. Ooh, and I wrote that down wrong completely, didn't I? 0.2773. So if I want to know how many grams of the Al2S3 were left over, then again, I'm just going to convert this over to grams now. So I would multiply my 0.02773 times the molar mass of aluminum sulfide, 150.158. So I would see that I have 4.16 grams of the Al2S3 left over. And so let's just do one final check that I also like about this problem. And so remember, the law of conservation of mass tells us that matter can't be created or destroyed. And so the amount of matter that we have in the beginning has to be equal to the amount of matter that we have at the end. We're told in this experiment that we start with 25 grams of aluminum sulfide and 15 grams of water. We start with 40 grams total. So at the end, we better have 40 grams total, spread out amongst all the different molecules or all the different compounds in our reaction. And so sure enough, I just calculated that we have 4.16 grams of aluminum sulfide. So that's how much of this reactant we had left over. We have no water left over. But if we take that 4.16 grams of aluminum sulfide, add the 21.65 grams of aluminum hydroxide, and add the 14.19 grams of hydrogen sulfide, sure enough, that adds up to 40.00 grams. So we satisfy the law of conservation of mass. We check our answers, and we see that we are, sure enough, we are correct. So I know that the table is a much longer, much more drawn out process than the other two that I showed. But the thing that I do like about it, and the reason why it is included in some of your homeworks and why it will be on the test, is because it does give us a way using this table to calculate the amounts of everything that is in the equation, including the amount of excess reactant. It gives us an easy way to do that. And so I like that. That is a powerful tool to have in our tool belts. And so lastly in this lecture, let's talk about reaction yields. And so everything that we've calculated so far, when we do a more straightforward stoichiometry problem, or if we're doing problems with limiting reactants, what we are actually calculating there is what we call the theoretical yield. That theoretical yield is the maximum that we would expect to be able to get based on how much material that we're actually starting with. The reality is we're never actually going to make that much. If we were to take this into a lab, if we were to take this one here, so if we were to actually react aluminum and oxygen together, if we were to take our 50 grams, mouse is going nuts, but if we actually took our 50 grams of aluminum and 50 grams of oxygen, we're not going to make the 94.3. There's a few reasons for that. One is that we don't necessarily know that this reaction goes to completion, so to speak. And that's a topic that you'll get into, those of you that go to 115. Going on to CHY 115, you'll see that not all reactions actually completely go to completion. And so this reaction might not do that. There are also the realities of just how the experiment is actually carried out and how we recover this material. Those of you that go on to OChem and you're actually going to be making a lot of compounds in that lab, we'll see the challenges associated with that. You might make a lot of your actual product, but then you have the challenge of actually recovering that. You have the challenge of getting that and purifying that, getting rid of everything else that was there, drying it because the reaction probably happened in water. There's a whole host of things that are then connected to actually being able to collect your pure material when the reaction is over. And so this 94.3, that's the maximum that we would expect to get, but we're just not going to get that for a variety of reasons. So the amount that we actually do recover, the amount when the experiment's all said and done and we have our product in our little vial, the amount of it that we actually have is the actual yield. And so we're always interested then in just how efficient is the process. We want to compare the amount that we actually get to the amount that we expected that we might be able to get. And that's where this percent yield calculation comes in. So we take the actual amount that we were able to get in either grams or moles, doesn't matter as long as you're consistent, the actual amount that we had divided by our theoretical amount, and we multiply that by 100. And that's our percent yield. Keep in mind, this is very different from percent error. This is not the same as percent error. Percent error, which you talked about in lab a little bit, and we talked about it a little bit in the lecture in the very beginning in Unit 1. That's when we're comparing an experimental amount or an experimental measurement to a known. For instance, if we're measuring the boiling point of water, we know that to be 100 degrees Celsius. We do an experiment, we find that it boils at 95. We can calculate a percent yield on that, or sorry, a percent error on that. This is not the same thing. Percent yield and percent error are not the same. Percent yield, we're looking to compare how much we actually got to the theoretical maximum that we could have got. So again, just to recap that, the amount that we would predict based upon our stoichiometric calculations, so based upon the calculations that we've been doing, that's the theoretical yield. The actual yield will be less than that. Again, for a number of reasons. Maybe you've got some impure reactants, something going on there. Maybe there are byproducts that are produced that we don't represent in the actual equation. The reaction might not go to completion. We might not be able to collect all the material. Some of it might literally go down the sink. Any number of reasons. And so we can run our percent yield calculation. So go ahead and try this problem here. And so earlier we had predicted that our theoretical yield from our aluminum and our oxygen was 94.3 grams. Let's say we actually collected 48.5 grams. Calculate the percent yield. So go ahead and pause the video now and calculate our percent yield of this reaction. Easy enough calculation. So our 48.5, our actual yield, divided by our 94.3, gives us a 51.4% yield for this reaction. And so here's a good practice problem to go through everything that we've just talked about. And so if I have 10 grams of gold and 10 grams of chlorine, and I seal those in a container and I heat it up until my reaction is complete, my product is gold 3 chloride. So I want to know what the limiting reactant is, what the mass of gold chloride formed is, and what is the mass of our excess reactant that remains. So remember your basic strategy here, so yeah, your basic strategy is to do some comparisons to find out what our limiting reactant is, base your theoretical yield on that. We talked about a number of different ways. You can either use the BCA table that we discussed, or looking at the other methods that we did go over. There's a couple other little tweaks. I'm not going to go through them here. I would encourage you to try this problem. But then I would also encourage you to watch this video it's one of the supplemental videos that I made. And this, beginning at about 8 minutes, I go through this problem just as written. So I go through this problem in this video. And so again, that is one of the supplemental videos as well, just to remind you where that is. If we go into Unit 2, our Unit 2 materials, supplemental videos. There it is, stoichiometry, limiting reactants. And so starting at there it is, starting right at 8 minutes, I go through this exact problem. And here's another one that I would encourage you to try. And so we're going to determine the limiting reactant when 5 times 10 to the third grams of silicon dioxide and 5 times 10 to the third grams of carbon react. We want to find the theoretical yield of silicon carbide. So go ahead and pause the video, do whatever you want to do to try this problem, and I'll show you the answer in just a minute. Hopefully you really paused the video and tried this and came up with the fact that SiO2 is our limiting reagent, and 3.34 times 10 to the third grams of silicon carbide will actually form. Here's a last example. So an example using DDT, a very dangerous insecticide, been outlawed by the US government for quite some time. But here's how we can actually make it. So we've got our chemical equation here for the formation of DDT. So we have some amounts here of the various reactants. We see how much DDT is actually made. And so from that, you want to determine what the limiting reactant is. Based on the limiting reactant, calculate the theoretical yield, and then calculate your percentage yield based upon the actual that you're given here. Pause the video now, go ahead and try this, and see what you can come up with. Hopefully you were able to find out that chlorobenzene is our limiting reagent. Your theoretical yield is 709 grams of DDT, leading to a percent yield of 71.5%. And then lastly, just another example here. So go ahead and read through this on your own, and then pause the video, see if you can come up with an answer to this problem. Hopefully you came up with N2 being our limiting reagent, the theoretical yield being 60.6 grams of NH3 for percent yield of 49.5%. Now I know that those examples and everything that we just went through it's not easy stuff, and I understand that. If you did have trouble with these example problems, another place that you can, one of the places that you can find some help for these is if you go to our Unit 2 materials page on the website. All those examples that we just went through that I showed you the answers for, this lecture examples video here, Goes through all three of those, goes through our silicon carbide example here. Is it kind of weird seeing me in two different places? I'm almost wearing, oh, nope, different polo. Thought it was the same shirt, but it's not. But there's our silicon carbide example, and I run through that. You've got your DDT example a little bit later on in this. Anyway, they're all there. And I use different methods in each of these examples here to solve the problem. I use, you can see for the silicon carbide, I'm using that have versus need ratio technique. For the DDT problem, if I remember right, I use a table technique. There it is. Nope, the silicon oh, there it is. The silicon carbide one, the same one again. But I show you the table technique for that problem, approached a little bit differently even. And then I go through the DDT. So I go through all of those lecture examples here. So I would encourage you to watch this video too. And now I know that's a lot. I know it's a lot of video watching. I know that there's a lot involved with this. And so take your time, go through it. We do have a little bit of time with this unit in general, where I'm going kind of slowly through this compared to what I have in the past, believe it or not. But go through those, watch those. The more that you watch me doing these problems, the better that you will get at them, the more you'll start to recognize what to do. And what else was I going to say? Oh, I completely lost my train of thought. Sorry about that. But yeah, but just make sure that you're watching these, that you're going through it and using all these different resources. The other thing that hopefully you've keyed in on, and that you'll see maybe when you watch that supplemental video, the lecture examples video here, and as I've walked through this, is, I mean, limiting reactants is just one concept, one idea about what is going to limit the amount of our reaction and basing our calculations on that. But there are many different approaches to it. None of the approaches are the right one, so to speak. Figure out what approach works for you out of all the different things that I've shown you today and all the different things in this other supplemental video. Figure out what approach works best for you and use that approach on these problems. There's no one correct approach. Any of these approaches that we've talked about will work and will get you to right answers. And so that is all for today. And so that will conclude this week's worth of lecture videos. And so as always, if you have any questions, make sure to email me, get in touch with me, let me know how I can help, and study hard. I hope everybody has a great day.